talk in the afternoon. Yipan will talk about hyperbolicity.
Hello everyone. The microphone works. Again. Hello everyone. Thank you very much for the kind invitation, and I'm very glad to speak at this traditional meeting. Wait, or like this? Yes. Oh yeah. Oh, sorry. I pushed to the mute side. Yeah, I'm very glad to speak at the traditional meeting in this wonderful place. And today I'm going to talk about quasi-periodic cocycles. Some of you may already heard my talk on reducibility. And today I will try to focus more on hyperbolicity of renormalization to better fit our theme beyond uniform hyperbolicity. So to start with, what is a quasi-periodic cocycle? A quasi-periodic cocycle, let me try the dots. Okay, it's here. So quasi-periodic cocycle is a pair. We have irrational alpha, and the second coordinate A is a one periodic map, maps in some Lie group G. And by saying quasi-periodic cocycle, we view it as a skew product. On the base map, it's a translation, and on the fiber, it's a linear map. So imagine we have a base map to be one-dimensional torus, and when we are jumping, and when we're rotating on the base map, we are jumping linearly on the fiber, which is a real vector space from W and goes to AXW. And on Tuesday's talk of Zaha, she already introduced linear cocycle with a shift base. And also there are people working with hyperbolic or partially hyperbolic base. And here, this irrational rotation is why this irrational rotation is the name quasi-periodic comes from. And of course, the dynamics of the cocycle is highly depending on the base, the base dynamical system, and also highly depending on the group we work on. So what can be the group? For example, it can be one-dimensional, compact or non-compact, where Yoko already did some part of it. And then people working on SL2R, which is the most studied case, I will explain soon the motivation, and a corresponding generalization, which is symplectic. And also we can go to compact groups like SU2 or SO3. And for such skew product, the dynamics, when we keep iterating on the base, it's just n times rotation, while on the fiber, we will have a shifted product. So it's AX times AX plus alpha, and goes to AX plus n minus 1 alpha. And why people working on these quasi-periodic cocycles? One major motivation is a close connection with spectrum of Schrödinger operator. So we talk about a discrete one-dimensional Schrödinger operator. It's defined from a square summable space to itself, un plus 1, un minus 1 plus a potential, and the potential is bounded. The interesting case is when potential is generated by some time-discrete dynamical system. And the most studied one is one-dimensional torus with Levick measure and irrational rotation. And in this case, we can define the potential to be fx plus n alpha at position n attached to a base point x. And then in this case, we will get a family of quasi-periodic Schrödinger operator. And to study the spectrum, we solve the eigenvalue equation. And then HXU equals to EU, you can write them clearly and get un plus 1 and un can be given by un and un minus 1. And the matrix before E minus Vx plus n alpha minus 1, 1, 0, we can see that in fact it's an SL2R matrix. And by changing n, there is also a shifting of alpha corresponding. So it naturally goes to quasi-periodic cocycle. And this one is called a Schrödinger one. And then for this cocycle, when we iterate, when we iterate, we will see, okay, the second coordinate, in fact, it will tell us from the initial condition u0 and u minus 1, we multiply the second coordinate, it will already provide un and un minus 1. So from the dynamics, it provides everything about the spectrum. So in particular, the famous Johnson theorem brings us close connection with hyperbolicity of Schrödinger cocycle and the corresponding spectrum. But let's stay with dynamics in this talk. So for two cocycles, when are they conjugate? Since we already view them as skew product, the conjugation will also given a skew product by 0b. Or we can express them clearly by the second coordinate. So it's bx plus alpha times a1x times bx inverse goes to a2x. And the special case would be when we are conjugate to a constant. That is what we call reducibility. And to include some special case, instead of requiring one periodic, there is a 2t here when we talk about reducibility. However, there are plenty of abstraction to get reducibility. For example, when we solve cohomological equation, there may be small divisor problem, and we will need to add more arithmetic condition. So instead of the strong reducibility, we also introduce an almost reducibility. So instead of conjugate to constant by one conjugation, we also allow a sequence for almost reducibility. We have a sequence of conjugacy to bring us to a constant. And the first local result is by KM theory. So when in the perturbative region, when we are close to some constant, KM theory may apply. In the quasi-periodic cocycle case, the study dates back to Dinenberg-Sinai, and the one we will cite later is given by Eliasson. So he showed that for Diophantine frequency alpha, as long as our analytic cocycle is close enough to a constant, then in fact it is analytically almost reducible. And here, Diophantine condition means that alpha is never too close to rationals. And and one last dynamical element I would like to introduce is Lyapunov exponent. As our cocycle alpha A behaves linearly on the fiber, the Lyapunov exponent is defined immediately by the log of norm of an go with space and time average. The limit always exists, and in particular, when it is SL2R cocycle, the value is non-negative. And then we may ask when it's positive or 0. And the result we will use later is Courtani dichotomy. So we start with irrational base, go with smooth symplectic cocycle, and a rotation. And the rotation to provide a monotonic parameter. The Courtani dichotomy dates back to the study of Courtani for M function, and then Simon showed it for SL2R cocycle, and then generalized to symplectic one by addition a few years ago. So they proved that for almost every parameter theta, the cocycle alpha R theta A has either positive Lyapunov exponent or it is L2 conjugate to rotation. And by saying rotation, it means cocycle value takes values in symplectic intersect special orthogonal. It's also because we always regard these Lie subgroups of general linear group. And in particular, in this paper of Dishon, he also showed the density of positive Lyapunov exponent. And there are also many people working in that direction, including positivity or continuity of Lyapunov exponents. And now, with all the preparation, we can move to renormalization. So what is a renormalization? Yesterday in Silvan's talk, we already started. So for example, we have a map, we have a manifold M, and we have an F from M to itself. In Silver's talk, he found a renormalization domain, D, and we talk about how F is going back to D. And that is an inducing problem, an inducing process. But then we will see that what we get is a map from M to itself and goes to D to itself. To make it an operator, we need to do an extra coordinate change so that gradually our map will go back to the same space, still from M to itself. And then, so that this coordinate change we will explain later. And then in this way, by staying in a same certain class of dynamical system, we make renormalization an operator. So itself may have some interesting dynamical property. And also, the dynamical behavior of the orbit along renormalization may also provide some information of the original dynamical system we start with. And one important property of renormalization is always preserves conjugacy. Let's go with cocycles. So two cocycles are conjugate if and only if their image under renormalization is conjugate. So this idea of renormalization operator, this idea of renormalization raised in many forms in mathematics and physics. To study renormalization in dynamical system, studied in the 70s by Feigenbaum, Coulette, Tracy, concerning unimodal map. And since then, there are many people working on it. And the case we are focusing on, the quasi-periodic one, started with Ekman Yocos when they studied circle diffeomorphism. And the one I'm going to talk about, the quasi-periodic cocycle one, is started by Hafez Krikoyan. So after the history, what is exactly renormalization of quasi-periodic cocycle? I have prepared the base map here. So in our case, renormalization is more from one-dimensional. And in our case, that's also why we require the base frequency to be in one-dimensional torus, not higher. And the renormalization is indeed defined accordingly. So to define a renormalization for the quasi-periodic cocycle, we first look at the base. We first look at the base. We start from point 0, and then we go to, and on the base we have a rotation alpha. And then we find a first last moment, A alpha. So by saying first moment is for any other integer smaller than A, they will stay further from 0. By saying last, it means A plus 1 alpha will already on the other side of 0. So we find this first last moment, A alpha. So A is in fact the integer part of 1 over alpha. But it's on the other hand of 0. We do a reflection and go to the same side. So inside 0 alpha, we find a smaller interval, and we draw them back to your line. So in 0, 1, we start with 0 alpha. And then this induction provides 1 minus A1 alpha. And then we do a rescaling. This is first part of the coordinate change. So we start with 0 alpha inside 0, 1. And then by first return, we want to stay on 0, 1 minus A alpha on 0 alpha. So we do a rescale to make 0 alpha to be 0, 1. And then we go here. So the rescaling will be 1 over alpha, and in fact, this is the Gauss map of alpha. And then this finishes the base point. So we start with alpha and go with a Gauss map of it. However, then accordingly, we can define it for cocycle. For example, here, so a formal definition using commuting pair, and I don't want to go into that much detail, but the idea is now by writing commuting pair in this shape, we used to define quasi-periodic cocycles to be one-periodic, but now by writing commuting pair, we no longer require A and B to be one-periodic. In that case, a cocycle is one-periodic if and only if it commutes with one identity. So that's the reason why we start with one identity, alpha A. So that guarantees the one-periodicity of A. And then we do the iterating. We find alpha and 1 minus A alpha for the first coordinate. So we will iterate the cocycle accordingly. And then we do the dilation. But then the issue is, after the dilation, we will lose the periodicity. By having two maps on R here, there are no more one periodicity. So the thing we do is we solve a cohomological equation on R to make the first line to be one identity again. And then accordingly, commuting pair guarantee automatically A tilde 1 is one periodic. And that's how we define renormalization operator. And the point is, the normalizing map is not unique. And that's also can bring quite some trouble. Yeah. Yeah, so the essential idea is always from the base. And then we move to renormalization. Then we move to renormalization of quasi-periodic cocycles. As an application, the result can always, by use of renormalization, the result we can get is always in a shape of global reducibility. And it's deep behind, there is a use of renormalization. So first result is started by Krikoran and finished by Frekchak. They showed that for alpha recurrent Diophantine and smooth SU2 cocycle, alpha A is either smoothly almost reducible, or they can conjugate to a very explicit model. It's alpha exponential 2 pi I dx plus c and exponential minus 2 pi I dx plus c. And here d is always some integer and c is a real number. And what is RDC? Recurrent Diophantine condition requires there are infinitely many elements in the orbit of Gauss map that belongs to a same class of Diophantine condition. And due to the ergodicity of Gauss map, it has Furlebig measure. And how they prove it? So in fact, in the paper of Krikoran in 2001, he firstly defined the renormalization of quasi-periodic cocycles, and he proved the convergence of renormalization of SU2 cocycles. And the convergence, and the key to prove convergence of renormalization is a so-called a priori bond. And here for SU2 cocycle is rather imaginable because the group itself is already compact. And then it moves to SL2R cocycle. So after Krikoran first introduced renormalization of quasi-periodic cocycle, later on Avila Krikoran, they formalized the definition. And in particular for SL2R, SL2R is only visible in the title. I forgot in the statement. So still, if alpha is recurrent Diophantine and A is homotopic to identity, I mean this condition is due to SL2R has non-trivial fundamental group. And then for almost every theta, alpha R theta A, it is either non-uniformly hyperbolic or analytically reducible. Oh, yes, thank you. Yeah, A is C omega. Yeah, I missed it. Yeah, so let me first state the other one. And then what about non-homotopic to identity case? What they proved is for any irrational alpha, A not homotopic to identity. If we start with L2 conjugate to rotation, then in fact we can show that alpha A is analytically conjugate to rotation. So what is behind the two theorem? So first, by Cottani's theorem, they already know that the essential thing, the condition they can start with is L2 conjugate to rotation. And that is what provides a priori bound and guarantee the convergence of renormalization. And then, depending on the homotopy class, when it's a homotopy to identity, and because of the L2 conjugate to rotation, in fact, the limit in SO2R, because of the low dimensional speciality of such group, as long as it's homotopic to identity, it must be a constant. So renormalization converge and bring it to the neighborhood of a constant cocycle. Then it is the region where KM can apply. And that's how they deduce reducibility. And on the other hand, when the limit is no longer constant, what can they tell? So in Avila-Kikuran 2015, they find another tool, monotonic cocycle, to deal with it and finally solve the rigidity problem without any arithmetic condition on alpha. And with all this background, now we can finally move to our results. So it has been studied for SU2 or SL2R, and here the result holds for quite general Lie group of we reviewed it as subgroup of GL general linear group. So the theorem states that still we are in the family of analytic, and for any irrational alpha, if we start with L2 conjugate to rotation, then we can find a sequence of Cn, and we can find a dynamical degree D, which we'll define soon, and an integer chi, so that the renormalization of iteration of alpha A goes in a very particular shape. So the first term is given by Gauss map of chi alpha. And then this phi n, in fact, goes to 0. So it becomes closer and closer to a model shape. And here we can see that by saying convergence of renormalization, we are in fact cheating a little bit, because even the model of, even this model, it itself is changing along renormalization. Like this D will go to minus D along renormalization, and C and alpha will change accordingly. But still, it's since phi goes to 0, the idea is starting from an alpha A L2 conjugate rotation, and starting from the model alpha exponential dx plus c, along renormalization, the orbit of the two will go closer and closer. So I will write this form down and for later refer. So our limit shape is this one. And what is the dynamical degree? So in previous, we can see that the shape, the limit form is defined completely. It's a linear form and is essentially depending on D. And what is D? The dynamical degree, in fact, is an average of growth of A. In fact, it's an average of growth of A. So what we do is we do the derivative in the algebra. We have an average for AN. And then the limit, and then we can always find the limit. And the limit dx, for almost every point, they stay in the same conjugate class. And in particular, they're in the compact part of the Lie algebra. And it has some periodicity. So up to some chi, the bound is always given by, is only depending on the group G. So up to some integer times exponential D equals to identity. And that is the dynamical degree of alpha A. So the limit is So the limit is purely depending on the dynamical property of alpha A. And first result would be the same. Since renormalization brings us closer and closer to this model shape, a first result would be when d equals to 0. Again, we are going to a neighborhood, arbitrary closed neighborhood of some constant matrix, of some constant cocycle. Then it's again where the local Km result can apply. And of course, the result, and as mentioned before, reducibility result is depending on arithmetic condition, is depending on the particular choice of Lie group. And here, for simplicity, we will stay in general linear group. So what we can show here is if alpha is recurrent definitely and d equals to 0, then the two iteration of alpha A is analytically almost reducible as a general linear cocycle. Here, one more thing to mention is renormalization preserves conjugation, so automatically it preserves reducibility. However, almost reducibility is given by limit, and in the definition there are two periodic map involved. So when in the future of renormalization we have something almost reducible, as long as there is two periodic in the definition, when we want to go back to read the original, to read information for the original cocycle, we will always need an extra two iteration. But it's very technical detail. And then if we are no longer, if we may not be in the neighborhood of constant, what can we tell? If we are in neighborhood of, if you are working with this alpha exponential dx plus c as limit of renormalization, what type of hyperbolicity we may get? So first thing, as I mentioned, along renormalization, alpha goes to the Gauss map. So in fact, from 1 alpha along renormalization, the orbit will gradually dance on T. And D, as I mentioned, it will jump between plus and minus D. And then C in fact is also changing. So to properly talk about hyperbolicity of renormalization, we first need to define a set, a proper set. So easier situation would be regular. As we have seen, let me write it here. So as we have seen, C is always in centralizer of D and intersect the compact part. So of course the result is imaginable to depending on symmetry of D. And we first work with regular D. Regular means the centralizer is abelian, so we denote it by T. And then the hyperbolic set K, we will take all irrational alpha, and D will be plus and minus D0, and T, since C is also moving around T, we take arity into consideration. And then this is our hyperbolic set. And how to talk about the hyperbolicity on it? It is something not easy. I want to stay here, so I remove this part. So in the space of all analytic quasi-periodic cocycle, in fact, what are they? The first coordinate is irrational rotation, and then the second coordinate is C omega h Tg. So when we go to the tangent bundle, the first one is doesn't matter, and the second one. So in fact, we are decomposing C omega h Tg valued in the Lie algebra. But there's something more I would like to point out. Our cocycle alpha in the neighborhood, we can always write in this shape. Alpha is exponential dx plus c and exponential phi. One point is the t part. So if we project phi, we think about the project of phi in the t part and do the integral, this constant in t. In fact, it can always be absorbed into c, into the t part. So it's natural that when we're decomposing the space of phi, we have a t individually. And then the other thing, and the other one, I will go one by one. So the idea is, it's kind of like normally hyperbolic, but the one coming from the base invariant set is not dominated by the stable and unstable, but instead, it is a direction that expanding the quickest. So like this is our renormalization. Let's draw renormalization, and this line represents the hyperbolic set K. Then to decompose it, to talk about the hyperbolicity. Because the K essentially, when we see them in the space of function, the one which is visible is T. So the first part T, we claim that is inside K. It's absorbed by C part, and that is the most quickest expanding rate, but it's invisible because it's in K. And then we have a real unstable direction, gamma t prime. Gamma t prime is of finite dimension, and the dimension, in fact, is provided by D. So we have a finite dimensional limit, and then the co-boundary. The co-boundary is a stable direction. So by the name co-boundary, you already know that it is those who conjugate to the model that stays on the stable direction. So it's when D regular, we have this very explicit hyperbolic behavior. However, when D is singular, it means the centralizer may be larger than the abelian part. We will have much more difficulty. The essential part is it is no longer T in the decomposition, but now it becomes Z. And we only have control on the T part, but so we cannot tell that too much about Z. But the stable and non-stable direction are still remains. And because of this stable and non-stable, we can still manage to tell something on reducibility under some special situation. So based on this hyperbolicity of renormalization, here is a conjugation result we are able to talk. So our first one is under the assumption that dynamical degree D is regular. So we start with L2 conjugate to rotation cocycle, and we assume alpha to be of bounded type. Then we have convergence of renormalization is exponentially fast. And we can indeed show that starting from L2 conjugate to rotation, we are indeed analytically conjugate to the particular form. So the idea is, by convergence of renormalization, you can see it here. So by convergence of renormalization, we are going closer and closer to the model. And of course, we will also have boundedness of renormalization. Then, as we have seen the very good hyperbolicity regarding regular D, as long as we are stay bounded, as long as we are stay bounded, we are stay bounded and close to the hyperbolic set. In fact, we have to lie on the stable manifold. We have to lie on the stable manifold, and that provides the convergence of renormalization. And that also provides on the stable manifold that with some extra work like KM scheme, we can deduce that alpha A is indeed conjugate to the model. And in the previous page, the convergence result and hyperbolicity, they hold for all irrational alpha. However, when it comes to final conjugation result, there are more estimates and we should be more delicate. We should be more careful. So here, for safety, we first go with bounded type. And then another part, as I mentioned, for singular D, even though we have not that good hyperbolicity, it is still possible. It is still possible with extra effort to find some reducibility result. And here is it. So alpha is still of bounded type, and we will focus on SP4. So make use of some special low dimensional phenomenon, and we require to be homotopic to identity. And as I mentioned before, regular D means the centralizer is abelian. So automatically, we can see that the regular D can never be homotopic to identity. So this is a pure symplectic case, a pure singular case. And what we can show is, starting from a one-parameter space, alpha R theta A will fall into one of the following cases. Either Lyapunov exponent is positive, or by Cottani theory, we are L2 conjugate rotations. And that's the starting point of the following two. In fact, the second case corresponding to D equals to 0. D equals to 0, then we can apply the local reducibility result directly and get analytically almost reducible. Or in the case when D is not 0, we will try hard with the weak hyperbolicity and still manage to show that alpha R theta A is analytically conjugate to the model. So in this shape, we have generalized the result of Avila-Krikorian for SL2R to SP4, and they are both homotopic to identity. Yeah, and the non-homotopic to identity case, some part of the regular case we have seen before. And then one last idea is about how we get this finite dimensional expanding. How we get the finite dimensional expanding? As I mentioned, this coboundary space we can see by solving the cohomological equation. And then how do we see T and gamma, and how do we get this gamma T prime? It is essentially because of D. It is essentially because of D. So when we are in neighborhood of exponential dx plus c, to have regarding this phi, we want to conjugate them to see whether we can go back to exponential dx plus c. And then we will solve, then the corresponding linearized equation will read psi x plus alpha plus phi x minus adjoint action of exponential dx plus c phi x. And then again, we are making use of the compactness of D and C, so that we pick up a good basis. WK, and because D has exponential D equals to identity, so it will provide exponential 2 pi I Lx plus lambda. And then finally we get this cohomological equation. So with an additional skew part. And then the one we are familiar with is when L is not zero. When L is not zero, formally we can always write it by Fourier series. But then we will meet the small divisor problem. And that's also how the centralizer of D get involved, and that's why regular D is always an easier case. And when D is non-zero, we can still solve it. We can still solve the cohomological equation, but we will have L terms non-zero for a coefficient left. And this L terms direction will be the expanding direction. So that is how we get gamma T prime. And one last thing to mention is when L equals to zero, even we can solve it, we will also have a constant part. So that is how it is also natural. Yeah, it is also natural to have a T here. Also natural to have a T here. And in particular, because of we have no control. When it's a singular case, we have no control on the Z part. That is, at this moment, renormalization, we cannot go beyond Km theory. And that's finished my talk. Thank you very much.
Any questions? Okay, Silvius?
Well, you mentioned that when you work on the higher dimensional torus, there is no renormalization scheme on TD when D greater than 1.
Yeah, at least you cannot define it like this, simply.
Because there are less canonical continued fraction expansion schemes in higher dimensions. So, but you don't know of any similar renormalization schemes in such higher dimensions.
Yeah. This part I'm not very sure. And the difficulty I can imagine is because for alpha A, when we want to iterate, the iteration can only take values in Z, so it's one dimension. And when alpha is of multi-dimension, maybe each coordinate of alpha requires different iteration. But in total, for the alpha A together, it's very hard to find a uniform one.
Okay. And most of the results you showed are for analytic cocycles. Are there similar ones, for instance, this uniform exponential convergence of the renormalization operator or scheme for more general cocycles that are not analytic in other classes of regularity?
Yeah, in our proof, we do use some complex analysis, but I believe similar result can be expected. Thank you.
I actually wonder, just after the question of Silvius came to mind to me, maybe it's known. Has anybody tried replacing the circle rotation with interval exchange transformations?
Oh, sorry.
The base, instead of taking a rotation on the circle,
Yes.
considering cocycles, but you take interval exchange transformations.
Oh.
Reducibility in general.
Oh yeah, I guess that's a good suggestion.
No,
Yeah,
not,
I haven't.
you never discussed
yeah,
this.
I haven't think
no.
about it yet. Yeah, but that's a good direction. Thank you.
There should be something, right?
So for example, back to people work on the Rosy cocycle over interval exchange map. They're doing this Rosy acceleration, and then the base dynamics is interval exchange map. And then that's some. Yeah, that's
But I was interested in reducibility. Yeah, okay.
Thank you.
Any further suggestions, questions? No, then let's thank you again.